So now that I have shown you that rotation around the fixed axis, like a relatively simple case, results in the spin angular momentum not pointing in the same direction as the angular velocity, now I will show you what is really going on in a more general case. So that's what we said in introductory physics. Now, the reality is that the moment of inertia I is really a tensor. And think of tensors for us, think of tensors as a matrix. Alright, let's say that I have my angular velocity vector and it has a non-zero x, a non-zero y, and a non-zero z component. And of course, L rotational, the rotational angular momentum is also a vector. So it does have an x component, a y component, and a z component. Now, okay, you're familiar with this notation of writing vectors. You've seen me doing this many, many times. This is not the only way of writing vectors. Let me show you another one. It's a different representation, okay? There is really nothing new. I can write it as a matrix. I can write a vector in the form of a matrix. This is what? This is a 3 by 1 matrix. Okay, 3 rows, 1 column. And I can do the same thing for L rotational. It does not include any new information. This is the same. The 3 components remain the same. I'm just writing the vector in a different way. And you will see why. Again, this is a 3 by 1 matrix. Now, what I mean when I said the moment of inertia is really a tensor, okay, this is it. It is a 3 by 3 matrix. So it will be a number here. It will be a number there. And there. And all of these are numbers, okay? I'm using symbol with subscripts, but at the end of the day, these represent numbers. And this is the moment of inertia tensor, or a 3 by 3 matrix. Now, let's see what we get. Okay, let's see what we get when we multiply the moment of inertia tensor with the angular velocity vector. So I'm gonna do I times omega, where I is going to be this matrix, and for omega I'm gonna use the 3 by 1. Now I do want to start. So if this I is a 3 by 3 and omega is a 3 by 1, okay, so I is a 3 by 3, omega is a 3 by 1, then the result is going to be a 3 by 1 matrix, which is consistent with what L rotational should be, okay? If you're getting anything else other than a 3 by 1, then how can that be equal to your angular velocity to your angular momentum vector. Okay, it has to be a 3x1. Now let's see how we're gonna do that. Okay, I'm gonna write again my moment of inertia tensor, and I'll show you the process. All right, and this is multiplied with omega x, omega y, and omega z. And let's make all of these into their matrices. So here is one, and here is the other one. Alright, now I'm multiplying the 3x3 matrix with the 3x1. The way to do it okay, as I said, this is going to be a 3x1 matrix, the result. So I will have 1, 2, 3 numbers. Now the way to do this matrix multiplication, the first number here is going to be Ixx times omega x. So I'm multiplying this number with this number plus this number with this number, Ixy times omega y, plus this number with omega z. So Ixz times omega z. Now this is going to give me a number, okay? It is, yeah, you do have to do a lot of calculations to get this number, but at the end of the day, this is a single number. Now, how am I thinking of this process? Okay, if I take this and I rotate it by 90 degrees, if you want, then I will have here omega x, here I will have omega y, here I will have omega z. So this product plus this product plus this product, that's what I need to use on the first row. How will I get the second number? I'm doing the same thing, okay? I'm rotating this by 90 degrees and bring it here. So I will have omega x here, omega y, omega z. Now this is, okay, this is just my mental way, if you want, of remembering how to do this matrix multiplication. So this will be Iyx times omega x plus Iyy times omega y plus Iyz times omega z. Now I want you to do the same process mentally. As I said, take this, rotate it by 90 degrees, and bring it here. You will get Izx omega x plus Izy omega y plus Izz omega z. This is the result for, okay, this is L rotational. It is a 3x1 matrix, so it is a vector. That's the x component, that's the y component, that's the z component. Okay, so what you see here, this is L rotational x. What you see here is L rotational z, and what you see here will be your L rotational y. Okay, it is indeed, it is more complicated. It is a more complex result than what we did in introductory physics, but a more an accurate way of thinking of the moment of inertia is not as a number but as a tensor or as a 3x3 matrix. In general, it is important to remember in general the L rotational, okay, L rotational points in one direction, and omega in general points in a different direction. Those two vectors do not point in the same direction.